Thank you for joining our webinar. We're going to get started now since it's 10 o'clock. And just wanted to let everyone know what you see up on the screen here. If you want to take a minute to use your phone QR reader to scan this QR code, this is going to be a worksheet that Henry is going to be talking about later on in the webinar that could be helpful for you. And we'll give some more information about that later. So Morehouse is a manufacturing company that produces force calibration equipment and adapters that are used around the world to measure force. Last year, we actually just celebrated our 100 years in business. We're really in the risk reduction business for force and torque calibration. And often what we've had to do is really have hard discussions with customers who maybe are confused or frustrated or just don't know about the importance of their measurements. So a little bit more about, if you want to go to the next page there, Henry, about us is we do manufacture calibrating machines. So the universal calibrating machine, deadweight calibrating machine, and portable calibrating machine. So if you go to the next page there, Henry, you can see some pictures of those. These are basically some of the solutions we have for labs that will help them to accurately calibrate their force measuring instruments. And the reason why we do this and why we're having this webinar today and why we provide these instruments is it really comes down to our purpose, which is to create a safer world by helping companies improve their force and torque measurements. So that's also why we're having this webinar today, just to educate folks, those of you on the call, a little bit more about force calibration. We do have capabilities at our lab here. We have two different labs. We have a force and a torque lab. We're a primary standards laboratory and offer deadweight calibrations up to 120,000 pounds of force known to within 0.002% of applied force. We also offer other force calibrations up to 2.25 million pounds or 10 meganewtons of force known to within 0.01% of applied force. In the torque realm, we also have the second most accurate torque standard in the world, which was purchased from the National Physical Laboratory in England. For torque, we have uncertainties of better than 25 parts per million. So that's just a little bit of background about us and what we do. And I also want to introduce our presenter today. Henry Zumbrun is the president of Morehouse Instrument Company. He's been the president since 2013 and has worked at the company for more than 20 years. Henry really has a passion for measurement accuracy, and you'll hear that, I think, today on the call. He has a passion for reducing risk associated with measurements that impact the safety in our day-to-day lives. One thing I've learned from Henry is just the far-reaching impact of force measurements on everything from the planes we fly in to the bridges we ride on and the cars we drive. So now I'm going to pass it over to Henry for the webinar.
Thanks, Heather. And the hotels we sleep in. So, or the Airbnbs we rent, or the condos we live in, as we have seen recently by certain instances. Privileged that everyone here is spending their time with us. I have went through the list as Heather was speaking. I was a little bit delayed as I was typing some response. So Heather, if you could post the link in the chat, we had a question about that. So we will post the link if people do not want to scan the QR code. That's much easier, I imagine, for most, and you get the everything on the computer. For those that are watching this on demand, they will have to use the QR code because there is no way to post a link to those that could not make it. So thank you all for your time. I'm privileged, as I said, to be joined with some colleagues, some fellow colleagues, some that were presenting at NCSLI the same time I was giving this presentation. So don't worry, this is not a direct rehash of that. We've added quite a bit to this, and after the discussion from the NCSLI presentation, we've taken some feedback and made it better. We are always accepting of feedback because it makes us better. So I'm going to stop my video right now. I wanted to keep that on to personally say things to people watching this, but I'm going to stop it because it consumes bandwidth on our end. Anyway, with that said, we're going to start this presentation. As Heather said, my name is Henry Zumbrun. I've been with Morehouse for a pretty long time. Over 2 decades now. The company's been in existence for over 100 years. This came about, this actual presentation came about because of 2 years ago at an NCSLI meeting, we were presenting TUR, paired test uncertainty ratios. And we had a discussion topic in one of our learning labs that questioned the formula that we showed on the screen and said, hey, we never saw that formula. And sure enough, about half of the group was divided about what we were presenting and teaching, and the division was on resolution. Should the contributors to the UUT's resolution, unit under test resolution, be included in the uncertainty that you report to a customer or in your decision rules? So went back pretty charged up after that. And we did see about a 50-50 split. So pretty charged up after that, and went and did a lot of research, wrote a paper, submitted to NCSLI, and hopefully that will be published, or you can get it on their site. We can certainly, you have the option to download it when you use the download link and sign into that. You have the option for a presentation, download a presentation, and do all of the other stuff. So again, happy you're here. My co-presenter at NCSLI that could not join us today was Mr. Dilip Shaw. He helped, I jokingly say, and which is more than true, most likely, he did about 90% of the spreadsheet where I did about 90% of the paper. So together, between both of us, we put in equal amounts, but just in different areas. And I'm very proud of the Excel sheet and the feedback and some of the stuff I got to contribute to it. And I was thrilled that he got to contribute what he did to the paper because he made it stronger. And shout out to some other people that helped with this paper and presentation. They were, a voice of reason, Greg Senker with IndieSoft, and Travis Gossman with Rockwell Collins also helped a bit, as did Heather, did an excellent job proofreading. So shout out to all of those people that helped along the way. So abstract. In the metrology community, there's an ongoing debate over which contributors to the unit under test belong in the expanded uncertainty calculation of the measurement process used for calibration. This is also known as calibration uncertainty, CPU. CPU is the denominator when calculating a test uncertainty ratio. So we all speak about decision rules and we hear about decision rules. Not all of them require a TUR, but if we go to JCGM 106 and we go to others, JCGM 106 mentions a TUR. Method 5, ANSI Z 540.3 handbook talks a lot about test uncertainty ratio and why we may use such a thing, a definition of such, to adequately, well, I shouldn't say words like adequately, but so we can properly define what goes into the numerator, what goes into the denominator, and we can report it. And we can all, by doing this, we can all speak the same language. So this presentation covers and uses examples that illustrate why best practices outlined in documents such as ILAC P14 and ANSI NCL Z540.3 handbook should be followed regarding contributors for the CPU. Instead of drafting their own test protocols and standards, calibration laboratories and manufacturers are advised to correctly calculate both uncertainty and risk. And I'm spending a lot of time here on the abstract because it's important to understand what that means. If we don't have rules in place and we're not following rules, is that a good thing or a bad thing? Right? And there's some people that are probably thinking, well, as long as you report to your customer what you did. Are our customers all educated? We have fantastic customers, love them to death. I can tell you, though, that not all of them understand this. So they are in metrology and they don't all understand it. So what happens when the next person, we do a calibration for someone that's, doing the working standards? Do we expect them to know and understand it? I know the standard's all about risk, and that's what we're going to talk about it. And even JCM 106 acknowledges some of these main issues. As it says, care has to be taken when such rules are encountered because they are sometimes ambiguously or incompletely defined. So we really need to all speak the same language, and we'll go over that. So this paper, hopefully, if you're interested, you can read it. Very, very proud of it. That is part of the downloads. And outcomes. Participants will review examples that illustrate how a device's resolution impacts risk and learn why outdated approaches to calculations such as test accuracy ratio must be discontinued. They will learn best practices outlined in guidance documents, policy documents, and standards such as ANSI, NCSLI Z540.3, ILAC P14, ISO IEC 17025 2017. We could add ILAC G8 to that list. And we will. I mean, that's going to be in the presentation as well. But I'm going to explain why I like ANSI NCSLI Z540.3. It's basically saying the same thing as ILAC P14 and G8, and I'll talk about that a little later. It's just connecting the dots a bit better. So start off with, generally, you can say there are more than 3 types of people in the world, but for this group, I'd say there's probably 3. Right? And the type of people, you can say, hey, I'm a pessimist. People have said I'm pessimistic when I speak about some of these topics because the assumption is a lot of people in the industry are not understanding these topics. And we see, I'm the one that gets all those calls, so I see all of those examples. So my truth, when I speak my own truth, is coming from my biased perception of what I experience and when I go out and talk to people. So other people may have different perceptions. I am more pessimistic that people in industry are not doing what is expected of them per the standards. And then we have the optimist, which is someone that says, hey, that's half full. And then we have a lot of people in this audience, the metrologist. We're not going to make any declaration of whether it's 50% full or empty. We're going to measure it. And we're going to measure it with a measurement uncertainty of what? 0.01% or whatever we have. We can all debate that. Reported probably at a 95% confidence interval. We're going to say it's 51.55% full, right? And we can all start thinking about that. But when we start thinking about that 51.55%, we have to ask some questions. Questions like, what is the definition of measurement uncertainty? Do we all agree on a definition? Is my definition different than Mike's definition? Different than Joe's definition? Different than, Heather's definition? I don't know. So what if we were asked to make a conformity assessment on our 51.55% half full with a measurement uncertainty of 0.01% of measurement? What if we are asked to do that? Are we all going to do it the same way? And a conformity assessment, the basic conformity assessment is pass-fail. If somebody said, hey, I need this glass to be over, 51.55% full, are we going to say at 51.55%, does it pass? They said over, maybe it doesn't. If they said over or equal to, would it pass? Now we have to consider the measurement uncertainty of 0.01. So lots of different discussion topics. Did we have a discussion with our customer on the appropriate decision rule to use for the conformity assessment? Probably not. This is me being pessimist coming out. But when we were at NCSLI and I asked an audience of people this one, I said, how many are having these active discussions with the customers? Not many hands went up. And during that discussion, did they ask to use a decision rule that might involve TUR or worse, TAR? Now I say or worse TAR, and I'll back that up later. I know many people use TAR. It can be used correctly, though we should abandon it, is my personal point of view. So the agenda today, decision rules, definition of test uncertainty ratio. What is it? Do we all agree on it? Evaluating global consumer risk, the effect of UUT resolution on risk and uncertainty. So we have these definitions of decision rules. There's more than 2, but ANSI NCSLI defines measurement decision risk as a probability that an incorrect decision will result from a measurement. And then ISO in 3.7 defines a decision rule as a rule that describes how measurement uncertainty is accounted for when stating conformity with a specified requirement. Slightly different definitions there, would you say? I like this picture from ILAC G8. I like ILAC G8 a lot. I actually like the old ILAC G8 a bit more, but that's just my personal bias to this. Probably not needed in this class, but this presentation. But this picture really captures things, right? When performing a measurement and subsequently making a statement of conformity, for example, in or out of tolerance, a lot of people use that, to manufacturer specification, issuing a pass-fail to a particular requirement, there are two possible outcomes. This is binary, right? Two outcomes, binary decision rules. The result is reported as conforming with the specification. The result is reported as not conforming with the specification. So here we have the illustration of risk, right? And you can see by B and you can see by A. The measurement, the location of the measurement, why I like this one so much is the location of the measurement is identical, right? On both of these examples. So we have lower limit, upper limit, and then we have an identical measurement, but B, about a third, maybe a third here, maybe less, depending on your calibrated eye. Maybe it's 25%. I tend to be, looks like it's over 25% to me, but maybe it's only 25%. About 25%, let's say, is hanging over that upper specification limit. Would you say it passes? Would you say it fails? Did you discuss your customer with what their risk tolerance level is? So then we have non-binary decision rules, and there's a cartoon we did because just poking a little fun at it. Because what essentially non-binary means, and this is in ILAC G8 2019, it means you could have an instrument, you're gonna pass an instrument, and then you can say maybe it passes, maybe it's intolerance, but we're not sure. It's up to you to decide. And then you have one like indeterminate fail. Maybe your instrument is out of tolerance, but it still may be okay for your application. Again, putting it back to the customer, and then you have the other one where it's completely out and it fails, but that's the cartoon we have, right? I would rather see industry, and I know this is another debate. I'd rather see industry just take a stance on it. Is it good? Is it not good? Have the discussion with the customer, find out what the risk tolerance level is. If it's 10%, great. You can say it's in or out to 10%. We don't have to do indeterminate pass fail, right? That's just an opinion there. But if we go to the ANSI NCSLI Z540.3, most people implement guard bands or using methods found in this handbook. I know there are other methods out there. There are people that are doing fantastic work. Shout out to best paper winner at Sandia, which is Colin. They have some phenomenal stuff going on there. People can go to their website and download uncertainty calibrators. NIST has the uncertainty machine. There's other people have written several papers on methods, Monte Carlo methods, and some other stuff. But it's out there, and ANSI Z540.3 handbook puts it all into one place, a lot of these, and they have 6 methods in there. Now, I talked to one of the authors, and he said he wished they could rewrite it today because they would handle things differently. But my bias is I tend to like pretty, defined rules that you can say, hey, I can point to this standard and say, this is what we're going to do. Are you good with it? Or a customer can point to this standard and say, hey, I want you to use guard band method 6 based on test uncertainty ratio. That's very easy. It's out there. The majority of people know it's out there. If somebody comes to you tomorrow and says, hey, I want you to do this method where you stand on one foot, hop, close one eye and look at, a 15-degree angle and then read the instrument that way. If they gave us a documented paper, how would you achieve it? If you're programming it, programming is expensive, especially if you have database and software and everything else. To add a rule that's really not vetted, or maybe that customer did vet it, it's just a mess. So I tend to really like method 5. It's overly conservative, but that's okay. Method 6 is good. Method 2. Really, method 2, 5, and 6 are pretty easy to implement per ANSI Z540.3 handbook. And what NCSLI Z540 talks about with guard bands is it's used to change the criteria for making a measurement decision, such as pass or fail, from some tolerance or specification limits to achieve a defined objective, such as 2% probability of false accept. The offset may either be added or subtracted from the decision value to achieve this objective. But now we go into ISO 17025, section 7861. This is an example where we like method 5. We use method 5 by default because most of our customers say, hey, just subtract the measurement uncertainty. And that's really what we're talking about when we say method 5. And because we do not have that conversation with everyone, we put it on our quotation by default, right? What we're going to do to comply with section 7861, which says the laboratory shall document the decision rule employed. And if you look at the thing, what we say here in our quotation, instruments which have a specified tolerance will have a guard band applied per method 5 of ANSI Z540.3 handbook. Sending an instrument in for calibration is acceptance to this quotation at Morehouse terms of sales referenced above. Now, we take pride and a core value in positive customer experience and working with our customers. So our goal is to offer other methods. Our goal, and I want to be clear on what the goal is. Our goal is to work with customers, educate customers, and offer other methods. Our goal is not to find the method where the instrument passes, right? So if up front someone wants to use method 6, that's fine. If up front someone wants to do something else, that's fine. Though by default we found most people are generally accepting of method 5, even though it is very conservative. And what is method 5? It is a simple approach to guard banding to calculate acceptance limits by subtracting the 95% expanded calibration of process uncertainty from the tolerance limits. This is an approach recommended by the ILAC G8 and various other documents. Now, this was the old revision of ILAC G8 that recommended it. And then it goes on. If the measurement result is within such acceptance limits, the PFA is very small and therefore assured of meeting a 2% PFA requirement. The only information necessary for this guard band approach is the tolerance and the calibration process measurement uncertainty. Boy, that sounds real easy, doesn't it? Until we get into definitions of TUR. Now, there are several documents out there. There are 3 documents that reference TUR, 2 that more than 3 that reference TUR, 2 that define it. Well, I have to add the well because I know ASME says N1 and some other things, and there's other documents out there. I do not know all of the documents, though I know if we start combing through them, you will see JCGM 106 only not defining TUR, only mentioning it, and you will see ILAC G8 2019 defining it, and you will see ANSI NCSLI Z540.3 defining it. ASME will give some guidance, and JCGM will give some guidance. And I'm sure there's other documents out there that are giving guidance. But if we look at it, the ratio of the span of tolerance of the measurement quantity subject to the calibration to twice the 95% expanded uncertainty of the measurement process used for calibration. I really like what ANSI did. So we'll discuss what ANSI did, Z540.3 did in more detail. And basically it says for the numerator, the tolerance should be used. There's a simple formula per the handbook. It says, hey, we're going to use the span of the tolerance. Pretty easy. And then for the denominator, it says, hey, the 95% expanded uncertainty of the measurement process used for calibration following the calibration procedures to be used to calculate TUR. If we go to the highlighted section here, it says that includes the influence of the item being calibrated, except for the bias of the MNTE. The calibration process error therefore includes temporary and non-correctable influence incurred during calibration, such as repeatability, resolution, error in the measurement source, operator error, error in correction factors, environmental influences. That's really what drew that 2-year ago thing, where half of the group says, hey, if I put the resolution of the UUT in that divisor, my uncertainty gets big. Yes, it does. The definition is there. ILAC P14 further says, and this is section 5.4, further says, the uncertainty shall cover the same contributors to the uncertainty that were included in the evaluation of the CMC uncertainty component, except that uncertainty components evaluated for the best existing device shall be replaced with those of the customer's device. So what do you think is in that same contributors to the uncertainty that were included in the evaluation of the CMC? Resolution? You think an auditor is going to come in from any lab, and if you're doing your measurement uncertainty budget for your instrumentation and say you can throw out resolution? The answer should be, well, if we've deemed it insignificance and repeatability is large, this is going back to the Excel sheet, then maybe we can. Maybe they can, but we have to prove that it is not significant. So here's just a word art. If we start looking at these standards, ILAC, P14, we look at G8, we look at ANSI, NCSLI, we start looking at all of these, but really we look at the two standards and look at the definitions of TUR, and you see some words that are found, short-term contributors, but resolution keeps coming up when we look at this. So, and you look at TUR and conformity assessments, you can see here the calculation of TUR is crucial because it's commonly accepted practice in making a statement of conformity. When used, here's my contribution to this is basically when used with the measurement uncertainty and the location of the measurement, really when used with the measurement location, one can calculate the measurement risk. So moving on here, accreditation bodies recommend requirements to contributors to measurement uncertainties. So global consumer risk. Defined by JCGM 106/2012, the role of CPU in conformity assessment is defined as the probability that a non-conforming item will be accepted based on a future measurement result. Looking at this, if we look at it, what if we don't all use the same definition? What if one lab does not use resolution of the UUT, right? What if one lab does not use repeatability? Our definitions are different. What happens? And if only one tier of the calibration chain cares about the measurement decision risk, then the whole process is at risk. When this risk is propagated throughout succeeding tiers, can we expect things to work properly? Read a lot of books, and one of my favorite books is by Henry Petrovsky. Petrovsky wrote a book about a pencil. It's a pretty darn good book about a pencil, but this one's really, really good. It was written around the 80s, but he talks about the roles of failure and successful design. And his quote here is really interesting because if we go back to things like the BP oil spill, if people remember back in 2006, an idling truck ignited so many gallons of diesel that it blew up the BP refinery, which was over $1 billion and several deaths that did not need to occur. And when we go back and we look at what happened with the BP refinery, you can actually pull case studies and trace that back to equipment that was not calibrated properly. Or equipment that was not maintained. But what Petrovsky says here, he says failures appear to be inevitable in the wake of prolonged success, which encourages lower margins of safety. Engineers and companies who employ them tend to get complacent when things are good. They worry less and may not take the right preventative actions. The reason this slide is in here is because when we pass things to general industry, a lot of these companies, not all of them, but several of them, and we can see throughout history, become kind of complacent until something catastrophic happens that forces change. So, and I'd say, the question is, does anyone feel that this may describe what is happening in metrology community today regarding the evaluation of global consumers' risk? Right? So we have this definition of CPU, which establishes whether relevant uncertainty contributors of the customer device will be considered by the calibration laboratory that is calibrating the equipment. If a calibration laboratory does not include these uncertainty contributors, then they are passing the risk on to the customer or consumer because the laboratory prefers not to retain the risk. This is often done without the end user's knowledge. We're gonna show an example of this. And then, like I said, most likely a general industry manufacturer will not calculate the measurement uncertainty associated with their measuring equipment. Although they bear some responsibility, they may not understand their equipment or how to calculate measurement uncertainty The measurement community has spent decades putting proper measurement and uncertainty practices in place. However, the general industry manufacturer is lagging decades behind these practices. And that's what we see everywhere. We see something, we're going to make a change today to a standard. How long does it take before people start asking as a general question about decision rules? Lots of presentations on decision rules, but how long? The standard came out in 2017. We're 4 years, almost 4 years in November. How long before we start having more than handfuls of discussions per year on decision rules? At least that's what we're on our end. I mean, maybe some of you out there are having, discussions every day on decision rules with customers. I don't know. All I know is our truth from what we see and from what I talk to. So I welcome feedback. If people have those discussions, if you're one of those, you want to send in the group tasks that, as a standard procedure that we are asking every customer that comes through, we're asking them about the risk tolerance and the decision rule and all that. That'd be great. It'd be great to hear some feedback to that. Hey, we are actually doing this and it's working well, or we have to educate every customer. Whatever it is, it's great to get it out there and we can all learn from each other. So, example, many in general industry, here's what we see, our truth or my truth. Many in general industry are still using outdated concepts for test accuracy ratio. So many, if we don't have to go that far, but we can say there are still POs being issued that talk about NIST traceability. They might say nothing else other than, hey, I just need a calibration that's NIST traceable. Is that okay? Most of us know now that our measurements are traceable to the SI. And they can be traceable through an NMI such as NIST, but they're not traceable to NIST. If you contact NIST and have a discussion, you will raise a lot of eyebrows when you say NIST traceability. Depending on who you get, there are people out there that have written several articles for NIST, and you can go to the NIST website and they have very, very good articles on traceability and their guidelines. But yeah, many in the metrology community have moved away from these terms, but both are still implemented in a lot of places instead of sound metrological practice. Many do not agree on what contributors should be included in measurement uncertainty evaluation. Some argue that the UUT's resolution does not need to be included in an uncertainty evaluation. Some write new standards that say, hey, no, we just need environment and repeatability. Repeatability will capture it. However, that's great. Repeatability is going to capture it. What if my repeatability is 1% or 10% of my specification? What if my repeatability, my resolution, what if my resolution, I have a 100-pound device and I set the resolution to 10 pounds? What if my resolution is 10% of the spec? And I claim, and the manufacturer sets the tolerance as 1%. Is that okay? It should repeat all day long. The standard deviation from a repeated measurement should be perfect. So it's things we need to consider, if we look at this is from LAB 48, UCAS LAB 48, a document I like. This is an accredited body for the UCAS, so it's not over here. Though they wrote a very excellent document here. And it says, in such a scenario, a calibration laboratory cannot make a statement of conformity or pass an instrument without violating ISO IEC 17025, because it defines a decision rule as a rule that describes how measurement uncertainty is accounted for when stating conformity with a specified requirement. Some may argue that you can take it into account by ignoring it. So, as metrologists, most of us are, I have to ask, right? If we can take it into account by ignoring it, can we also choose as a community, this knit group right here, can we choose, hey, I can take that red stoplight into account by ignoring it? Can we do that? What happens if we all do that? Do you think we're all going to be, the next webinar, if we decide to do that for a month and everybody's going to come back to our next webinar, do you think all of us will still be here if we choose to run every red stoplight? Probably not. So I said about my example. So here's an example. This is Jared. He's our production manager here at Morehouse. Excellent production manager. He knows some things, lots of things. I can get on a rant about tolerances and everything else with him. I can get rants on uncertainty. My recent rant on uncertainty has been on torque arms. If you have a specification that you have to achieve so much and you have a square drive, and that square drive has a lot of chatter, can you accurately measure your center distance? How well can you measure that center distance? If my chatter is 3 thousandths on a 2-foot arm, what's the uncertainty contribution of that? So these are things we discuss and think about. But anyway, we're thinking Jared's making a measurement with a caliber and a micrometer. They're 2 different resolutions. Jared is using a caliber to make a measurement. The drawing specification this is a ridiculous specification. We choose it, normally it'd be plus or minus 3 thousandths or 5 thousandths. So, but we're going the extra. So the drawing specification is 0.005 inches, and the user has a caliber and wants to know if the part is within tolerance. So someone just spec'd a super, super tight tolerance. Is Jared? Would Jared know to shrink the acceptance limit on the drawing so he can say with little doubt that the part is in tolerance? Or is he going to grab a micrometer? Knowing Jared, he'll grab the micrometer. But this is the thing, in general industry, will someone, if looking at a drawing and you see a tolerance like that, are they going to shrink it? Or are they going to say, hey, my measurement uncertainty on this is plus or minus half of this. So my tolerance, when I measure this, it really needs to be half of what the drawing says. Are they going to do that? Is anyone actively seeing people do that in industry? Some of them, they just may not understand the decision rule and what it means for them. Are they comfortable with a conformity assessment that does not include all necessary uncertainty contributors, such as the device's resolution? Do they want a statement that says pass with a sticker that allows them to use the device to make measurements? Are they aware of potential risk? All questions, right? Are they good questions? I don't know. We should, as a community, we should probably start pulling general industry. But here, I was talking about it earlier. So you have the effect of UT resolution and risk on uncertainty. So you have the resolution. This is a 1,000 kilogram Morehouse cell and varying the indicator resolution. And you can see the effect on total risk here. The risk starts to increase quite dramatically as the resolution increases. So does the overall uncertainty. That's this picture here to the left over here. And then this picture on the right shows the uncertainty percent contribution. So you can see different percentages. When our resolution on this cell is 0.001, that's a lot of counts. The resolution percentage, most could probably agree that 0.13% is insignificant. However, if we change the resolution here to 0.01, this is more common. This is probably what the resolution is going to be set at, 0.01 or 0.02 or 0.05. But when you look at it, now the contribution to the measurement uncertainty is 11.52%. The CMC contribution, 88.48%, resolution 11.52. And if we look at this graph, you can see how the CMC, that's our calibration and measurement capability. You can see how these graphs kind of cross and form the X here, where resolution starts to become dominant and the measurement capability, calibration measurement capability uncertainty shrinks. So very impactful to look at the graph and see what this does. We should all be looking at resolution and figuring out, is it significant or not? If adhered into common practice of requesting of TUR of greater than 4:1, other guides and standards may say 3:1. They may say other things, recommend different ratios. If we do that, before making a statement of conformity, then the proper formula for TUR must be followed. That's my statement. If we're requesting it, if somebody comes in and says, I need a TUR of 4:1, we should be using that formula. We should be using the right definition in that formula, which includes the resolution of the UT. And then JCGM 106 states, care is to be taken when such rules are encountered because they are sometimes ambiguously or completely incompletely defined. And I read that earlier and reading it again, and it's because they are. Right? If we just have this, are we paying attention to the location of the measurement? Are we just saying TUR of greater than 4:1? Do the customers know what the definition is? All of our laboratories that are out there making calibrations, are we all using the same definition of this? TUR cannot be the ratio of manufacturer's accuracy tolerance to the reference standard uncertainty. That's per both of these definitions. People use that. They say, hey, here's a tolerance. I'll just divide it by my MU. Great. What does that really tell us? Here, you see when resolution is considered, the TUR starts at 6.25 to 1 with a UUT resolution of 0.001 kilograms, and then declines to 0.17.1 with a 1 kilogram. When the resolution is not accounted for, the TUR ratio stays at 6.25 to 1. So depending on our definition here, I can say, hey, I'm just going to ignore the resolution. I got 4 to 1. We're golden. Let's do it. Right? If I do not ignore resolution and use the proper definition, now I can't say that. Depending on that resolution, I might be nowhere near 4 to 1. I might not be 1 to 1. I might be at 0.17 to 1. And there's another graph. These graphs are all generate on the Excel sheet, which I'll show in a moment. But yeah, here you can see the effects on expanded uncertainty here, with the differences of resolutions. And you can see as resolution increase, so does expanded uncertainty. Another graph from another image from ILAC G8. I like this one a lot because it says, hey, I have a small relative expanded uncertainty. With that, I have a much larger, look at this, acceptance interval than if I have a large relative expanded uncertainty. The caveat is, what is that definition of measurement uncertainty? What are we using? If we compare that to things we do here at Morehouse, this is dead weight, right? And if I look at this calculation here, you can see nominal value, measured value. I chose a measured value that's 10,000. This is a 10,000 pound load cell with a 0.1% of full scale tolerance. But you can look at the contributors here and you can say, hey, TUR here, 13. TAR, look at this. This is a great number, 62.5. And then this concept, this CPK, this is taking this is a process capability index for the statistical people. This is basically giving you insight as to the location of your measurement. We can see this graphically, but if you didn't have the graph, basically the way CPK is used, if the true definition is if it is 1.33 to 1.66, you're supposed to look at your process. If it's higher than 1.66, namely if it's 1.67, the process is considered to be in control. And if it's lower than 1.33, you really need to dig into your process. But it gives us a relative of, if this number here is above 133, we're pretty sure that our measurements are going to be good with all things considered. And then you have down here a simple guard band and 2%. This, if you want to mark your calendars, and Heather can put it in the chat window for anybody that's attending, and those that are online, mark your calendars for December, visit the website. This PFA, these graphs and stuff, we are developing a downloadable form that will be given away with that webinar. It's going to have TUR, TAR, CPK, method 6, lots of different things. Really excited about it. I keep tweaking it. I have hours and hours and hours on it. You can put in your appropriate risk level, do all kinds of things. So looking back, global consumer risk, what happens in the scenario where the lab asks for a TAR of 4 to 1 or some other arbitrary number? Some say they have evaluated their level of risk, though maybe they have, maybe that's okay for people. Though we have to question if they have. If somebody says, hey, I need a TAR of 4 to 1, they're not paying attention to the location of the measurement. Are they or are they not? These are questions that, hopefully auditors are going in and asking, well, hey, why'd you choose 4 to 1? It might be okay. I don't think it is in general. The general thought is if the lab performed the calibration set standards at least 4 times better than what they are calibrating, that everything is good. Is it, after today, you really need to start considering, more? So evaluating consumer risks. This is testament to the location of the measurement. You can see here, CPK dropped to 0. Our location of the measurement changed in this scenario. We had a measure value of 10,010. Total risk 50%. This is assuming that we're doing all this at CPK is at 3 sigma, but this is at 2 sigma. So we're plotting this out and saying 50% of the curve at 95% is over. That's what we're doing. I know some people like to reduce to 1 sigma. That's fine, whatever method you use. But even if we have, in this scenario here, it's on the line, right? And now this next scenario here, I've shrunk the uncertainty tremendously, and I have moved our measured value, assuming that we'd have resolution of 0.1 instead of 1 pound. Change the resolution, shrunk them, and have a measured value that doesn't round to 10,010. Another important thing on manufacturers and resolution and what it can do. So if I have a 0.1 resolution instead of 1 pound resolution, and instead of rounding to 10,010 and having 50% risk at 2 sigma, I could effectively read this at 10,009.6 and still make a conformity assessment. And here's a situation where the TAR was 58.789. We use dead weights on this example of 0016. TAR stays at, regardless of whatever I do in all these scenarios, TAR stays at 62.5 because it doesn't consider much of anything except for the measurement uncertainty. And then CPK was 1665. So already discussed what CPK is, but it measures 2 things well. And the summary is how close the mean of the readings are to the center of the lower and upper spec limits, how widely spread the readings are. And there, if a CPK is less than 1.33, it will need some action, different vendor, different vendor with lower uncertainties, better resolution, adjustments to the instrument, a more repeatable process. If CPK is higher than 166, it's really likely everything is good. However, you got to watch because the location of that measurement is in there. So it could just be, hey, I just need that adjusted back to nominal. If that's the way you're reading it, if you're, reading the device nominally and not using correction factors, because anybody could use a correction factor. So here's a little bit about TAR. The reason ANSI Z540-1 is in there is solely because of the fact the story in 1994, the story that I heard from people that are still alive, by the way, is that the standard was written with TUR in mind, and at the last minute, an editor switched it to TAR. So back in 1994, they were discussing TUR, and it got switched to TAR. So both ANSI Z540-1 and .3, they both have been withdrawn, but just a funny poke that this is finally, we're nearing the end of TAR, or hoping that we're nearing the end. Test accuracy ratio, outdated calculation that is not sustainable. It is the ratio of the accuracy tolerance of the unit of calibration to the accuracy tolerance of the calibration standard used. It was supposed to be temporary until better computing power became available or better method could be developed. Before ANSI Z540.3 explicitly defined the equation for TUR, many were using TAR and TUR inconsistently. That goes back to Scott Mims's paper, one of the best papers out there, and it's called Measurement Decision Risk, the Importance of Definitions. Exactly what we're talking about. What is that definition for TUR? And Mims goes on and on in the page. It's just, I recommend anyone read that. And the next slide, I have an example of it. So many in the metrology community have invalidated TDR because it does not align with metrological traceable practices, since test value uncertainty TVU does not include essential uncertainties components such as the UUT resolution. It is more in unison with the outdated TAR. I know people that are on some of the ISO standards might have problems with that. Again, that's my truth. That's only my truth there. Test value uncertainty. People use their different criterias. though. I just don't see it. I don't see passing this risk to the end user. And if we look at what I'm saying there, is this sustainable from our process measurement? If TAR, if we need to go 4-to-1 the whole way through, it says if we start at 1 from our process measurement and go the whole way up, I need SI to be 1,024 times better, or those that want to go to NIST. I need NIST to be 256 times better than the process measurement. Is that possible? In some situations it is, in some it isn't. The definition of measurement uncertainty, where a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. This is great right here. I start the next level down gets larger, 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 larger. So it's propagated, and you cannot have an uncertainty in this scenario better than the lab that performed the calibration on your device. Fantastic. Just from one level to the other. And then here's a quote from that paper, Measurement Decision Risk, the Importance of Definitions. Scott, he provides an example in there. He provides several examples. Really great paper talking about Jerry Hayes, talking about everything, the history from Grubbs, Eagle, back, how TAR came about. It was originally 3-to-1 ratio. They made it a 4-to-1, and how it was supposed to be temporary. This is back in the 50s. We moved pretty slow. Back in the 50s, they said, hey, this is just going to be temporary until better computing power becomes available. So 60 years later, I have to ask, do we have better computing power than what we did in the 50s? Comparing this example with the definition of TUR in the ANSI Z540 handbook, remember, someone says I want a 4-to-1, but if we go with a handbook and we go with a definition where we all could apply that same definition, it produced a 1.5-to-1 ratio for the same measurement. Pretty significant difference right there. And there's several with other examples of, thread gauges. There's equipment that can resolve ridiculous, has great resolution, but the best calibration method to calibrate that equipment might be 30 parts per million, where the equipment by itself and the resolution could be 5 parts per million. However, there's not equipment good enough to calibrate it. So at some points, we are limited by how good that reference is. So conclusion on this, and then I'm going to go to the spreadsheet and play with that a little bit. Conclusion is OEMs can influence standard making committees to draft test protocols, which shift more risk to industry. However, does the practice comply with ISO 17025 standard and accreditation guidelines? The metrology community must recognize mandatory policy documents, ILAC P14, guidance documents such as ANSI Z540.3 handbook. These documents correctly define the calibration process, measurement uncertainty for calibration. If a device's uncertainty has 2 cores of resolution, then a device that does not subject the conformance decision to higher risk is needed. Furthermore, if uncertainty contributors are omitted at the OEM level of calibration, how will we predict global consumers' risk and adequately account for uncertainty in the measurement traceability chain? Currently, if someone says, hey, ANSI Z540.3 is withdrawn, that's fine. We have to, currently what we have in our community is something that many do not make that correlation agreement with, because we have standards ILAC G8 2019 and ILAC P14 section 5.5. So ILAC defines TUR, ILAC G8 defines TUR, and then ILAC P14 in section 5.4 talks about those short-term contributors and what needs to be included. So they're not all together. ANSI Z540.3 handbook put it all together nicely. And if you say it's withdrawn, I would say, hey, okay, that's fine. Your argument is good. We can say that, but we still need to follow ILAC P14 and ILAC G8. And by following those, we're back to that all but the same definition in the denominator. Best practices outlined in guidance documents and standards, they should be followed. Consider this: manufacturers and calibration laboratories that fail to correctly calibrate both uncertainty and risk on equipment used to test medical equipment, airplanes, cars, and bridges. So each and every one of you, how will you feel when you schedule your next surgery? How about sitting on a bridge in a a traffic jam on a bridge. I hate that. That's part of my peeve. I get really, really anxious on stop traffic both ways on a bridge. I hate it. And then, or experience mechanical problems on your next flight. None of us are going to be okay with what happens on some flights. If this if this happened on your next flight, you going to be okay with it? Will you feel confident that measurements were performed correctly and when applied will keep you safe? Or will you worry about your safety? How do you feel not, now knowing that someone may have failed to calculate implied decision risk correctly, right? And then here's the last one. This hasn't happened that long ago, right? Condo collapse. Did they get the concrete measurements okay? From what I did a little research on this, and what I can come up with is there's going to be a lot of attorneys involved, which we all knew. One of my, and it's going to probably take years to sort out. And above that, there's criteria after 1989 on what needs to be done. So any building built before 1989, what did they do? Did they follow the recommended procedures and the protocols? Did contractors take shortcuts? These are things we don't know. Did they do the right testing? Did they make the right, correct measurement of concretes? Did they do everything they needed to do to build these buildings? Were they checked? So having to question if the people making the measurements may have understood the calibration measurement process uncertainty does not boost confidence. Does it? Do we really trust? Again, the question is, who absorbs the risk? Is it us as the calibration laboratory, or is it the end user? Or is it a shared risk, right? I can say if we're not putting the contributors in per ILAC P14 in that section, are we doing justice to the equipment we calibrate? And are we reporting the right measurements? If I have made anyone convinced that we should follow the right definitions, I would ask to please join us in educating the people who underestimate the importance of following the standards, calculating risk properly, and using what was presented today. You can help create a safer world by taking a stance to calculate TUR properly. Basically, using the definitions that were agreed upon in 2006 and the definitions that were agreed upon per in ILAC P14, which is both the revisions. So that being said, now I get to try to find this.
Yeah, while you're switching here, Henry,
Yeah,
I'm going to just mention a few things in the chat.
Great.
I did put the date on there that Henry mentioned coming up in December. We don't have a registration link yet for that, but I did put the date and time so you can put that on your calendar. And we do have a registration page for our next webinar, which is in October 13th, how to lower your force uncertainty. And I did put a link for that in the chat. And again, if you have any questions, I do see one came up here. Henry, there's a question. I noticed you didn't mention ISO 7500 or ISO 376.
Mm-mm. Yes, that does not pertain. So when you follow, the only mention to other standards out there, as a good question. The only mention to other standards out there would be, committees draft these protocols. So did the committee take the appropriate actions and calculate, decision risk or risk properly? I can tell you ISO 376, ASTM 74, it's inherent to the standards. They built out trees, they built out pyramids, they determine lower limit factors. ISO 376 determines measurement uncertainties at different levels and different classifications that allows you to use that for different concepts. So that standard, I love the question because that standard has risk. Both of those standards really have risk built into them from all the measurements that you're making. And it's very clear what goes into your uncertainty budget. In fact, in 376, you're going to do repeatability, you're going to do resolution, you're going to do reproducibility, interpolation error. You have the option case C or D where you're going to do incremental loading and a creep test, or you're going to do, ascending, descending, and do reversibility error. So there are standards that take all of this into account. What we are talking about specifically here are when you're calibrating devices with tolerances, right? When a customer does not say, I need you to calibrate the device to ISO 376, E74, E24, 28, E18, all the other ones, or ISO 7500, when they don't specify that and they say, hey, this device, calibrate per manufacturer specifications, tell me if it's good or bad. If you get that, that's not enough. You really have to have more of a discussion with them. What we are discussing is when they say, hey, I have this crane scale, I have this gauge, I need it to be this accuracy specification, and I need a report in accordance with ISO IEC 17025, which we are supposed to ask the appropriate decision rule and agree on that with the customer. And then you are reading clearly based on the measurement error and those ratios that we are discussing here. But great question. Those standards have everything that ILAC P14. Both of those standards basically are accounting for everything that ILAC P14 is stating. And so other great guidance documents, JCGM, HOLA has R205. There's other ones, but here's what we've done that people can download. And if you look at this, anything in the lighter pink, you can change your nominal value. You can change your CMC. You can do lots of different things. You can correct for students T. There's lots of things in here. We can handle up to a sample size of 30. What this will do is it will randomly generate numbers, right? So I have this here, and it will randomly generate different numbers, or it should. Your copy will. And we can change things. We can change the CMC, we can change the tolerance, we can change, plus or minus the number of counts. And if we look at this specific example here, I have a 10,000 pound load cell. Morehouse did, the calibration here, 10,000 pounds times 16 parts per million. We put it in our big deadweight machine, which will probably be upping that uncertainty to 20 parts or 25 parts. Not because we need to, but because of when you have more room. That should be another webinar when you talk about proficiency test and EN ratios and whatnot. Because when your EN ratios are like 0.8, 0.85, you really want to expand your room. So, and just in general, it's not a bad thing to be a little conservative, to give yourself more wiggle room for maybe a new technician or something else. People make mistakes. So another important thing is to do gauge R&Rs and be sure to test the competency of your technicians. But anyway, so we do starting resolution here, and anything, as I said, anything in these boxes can be changed. But if you look at them, you can see the graphs here, CMC, percent contribution, repeatability. We're using Wells-Satterthwaite equation here, effective degrees of freedom. So when we start changing things, you can see that, degrees of freedom, repeatability, uncertainty. So depending on the sample size, you can see that change. And it will, like I said, it'll go up to 30. Ideally, somewhere around, if you're doing, people ask, hey, how many repeat measurements should I do? Ideally, the sweet spot is between 12 and 14. ASTM, ISO 376, I have, of course, much larger numbers than that in those standards. So it will do that. You can just sit there, you can play with all types of instruments, MUs, tolerances, and you can go upper, lower specification limits, different things. We can change this. Right here, we're at 0.1. We can change it to, hey, what if it's 0.01? What happens? Different things, CMC, percent contribution, repeatability, all that. Most of the time that's going to be more conservative estimate. Correcting for students T, that's another method that we can use. If you use the T tables, you can reduce degrees of correct for small sample sizes as well. Instead of multiplying everything by 2, you can correct for the small sample sizes, but the Welsh-Satterthwaite equation gives you what the appropriate coverage factor should be at K95. So, and there you can see, I have this one unlocked. You can see formulas in this one on what we're actually doing here. And then you can see the TURs on this line. You can see them shrink as that resolution. Effectively, what we're doing here is we're starting with a resolution of 0.1, then it goes to 1, 2, 3. We could start that at, more or less. And you can see that, graphs will change. And you could just do, if you're a manufacturer out there in the audience that are listening, you can use this. Hey, how good do we really need to make our equipment? So it'll randomly generate numbers for you, and you can say, hey, if we set our, resolution at 1, it's right here, it's 92.87% of the budget. But if we set it at, can get 0.1, it's 11.52. Maybe we do need to go, less. And if we do it at 0.01, now the contribution is only 0.13. That's more than likely, that's probably going to be insignificant for most. And then repeatability, like I said, it's generating random numbers there. So yeah, you can use this. You can see it here. I think I have to decrease it here for this to come out, but yeah. So happy to answer any questions. If people have this Excel sheet and play with it and find some things, Dilip and I are looking for feedback. Here you can even, measured value. What we're doing for the measured value here is we're taking the sample size, and you can also make repeatability better because it's random numbers. It's going to generate by whatever the starting resolution is and then round it. So if we do not make repeatability better, we give it a 1, you can see what happens to the, percent contribution here. Its repeatability is dominant the whole way through under this scenario. We change numbers around, you get different results. So again, graphs, TUR resolution, you can see starts real high, 61.85, ends at 3.46. You can see the percentage contributions here that I've highlighted, CMC, repeatability percentage contribution. If I go up and make that a little worse, you come down now, those numbers change. Repeatability percentage, 57.62. Resolution at 0.1 is 0.06. It's very insignificant in that figure. And then it becomes more 4.45. Now it could become significant. And what I have to add on that is some people, when you hear me say, 0.06, I don't know if it's significant or not for your process. I'm judging based on what we see. But what I can say is if you throw away a bunch of insignificant contributors, all of a sudden you may have thrown away a lot of the budget. If someone said, hey, anything below 5% is insignificant. What if I have 5 contributors that are each 4% and we threw them all away? That's 20% of my budget of my uncertainty that I've thrown away. So be careful on what's significant and what's not. Typically what we'll see people do is if repeatability here is dominant, like repeatability is 57.62%, then they're going to say, hey, resolution is pretty much insignificant in this because repeatability is capturing the contribution to resolution. But as we go on here, and why resolution should be included in that denominator, at least for evaluation's sake, as you can see here, resolution is so coarse that my repeatability contribution is 0. But if I threw out resolution here, I would be throwing out 99.69% of the overall contribution to uncertainty. And that's significant. I don't care who you are. We all should agree that is significant. So yeah, happy to answer any questions. Thank you for any feedback, negative and positive. Both are certainly appreciated. I hope I've made a convincing argument. And yeah, do you have some?
We do have a question from the chat. Did anyone from the Z540 committee provide another document that has the TUR clearly defined?
No. Thank you for that question. Very good question there. It is defined, as we said, in ILAC G8, and it is defined in ANSI Z540.3 handbook. Now, even though a standard's withdrawn, it doesn't mean it cannot be used. I know I sat in with the Z540.3 committee, and they're talking about some things. The general consensus is they don't want another standard. I also met with the person that's in charge of is part of the committee for ILAC P14, and said we should really get that definition of CPU, calibration process uncertainty, in there. And he said he would likely do that. So very, very happy that we could get that all in one document. Because again, it is, if you go with people that say, yeah, that's withdrawn, you have to make the connection between ILAC G8 and P14 to clearly define the measurement uncertainty. But I am very biased based on Scott Mims's paper and everything else that I've read and the history. And we are certainly a nation, at least some of us, we repeat things, and we don't need to do that here. I think we try to reinvent the wheel quite a bit. And if we're trying to reinvent definitions, they struggled with it. Mims's paper is just quite excellent on how they struggled with it and how in industry it was a problem before it was clearly defined. And then so it gets defined in 2006, and it takes, almost a decade till, 5 years from there till people are adequately using TUR. And then other standards are being written that say, hey, this resolution really, really swamps my uncertainty. I'm not gonna use it. So then you get on standards committees that draft these protocols, and we're just in an endless circle on who the heck is absorbing this risk. I still don't know. It's one of the things you think about in the different industries and different sectors, like who is absorbing it and do they understand it? So I don't know. We're on the Cal level, I can say what I said in the presentation, that there's a lot of people that just do not realize the risk that is being passed on to them. And maybe we need more of a grassroots effort to educate them. Maybe all of us, together can help educate, our customers and the customers of our customers. So, yeah, great question. Anything else? Anybody else have anything?
Don't see any other questions.
Okay, so we went over. I figured we would when I added this in. When we talked at NCSLI, it was about a 35-minute presentation with about 20 minutes on the spreadsheet. And here since I did the majority of that, I skewed it towards the 90, maybe the 90-10 again on this, because the spreadsheet is there. It is a tool. You can use it. Both Dilip and I have done things, and there's comments. You can click on the comments that can help you guide through, and you can just play with it, put in your own examples, see what it does.